Our fourth video for this week is about multicollinearity. Everything we've talked about so far leads us right to this topic. And the reason why it leads to this topic is before we talked about standard errors. And as you see, I'm scrolling up here and I'll show you that I have this shortcut here, VIF. So the standard error of B is a function of a ratio of dispersions between y and x and the square root of VIF. Now how does this come about? Okay. Well, let's look at what happens. VIF is a shortcut to a vital piece in our hypothesis testing that I showed you already, because the t is calculated by a ratio of the b, the partial correlation coefficient, divided by the standard error of b. So as the standard error increases, t decreases. Big T good means that we can reject the null and conclude that our regression parameter is significantly different from 0. Small t, bad. We fail to reject the null. When we fail to reject the null, we may fail to reject it for a whole host of reasons. And one of those reasons is multicollinearity. So multicollinearity, what it does is it increases our standard errors and decreases our t-values. And it does it very specifically through the calculation of the standard errors. But then I oftentimes get from students what the correlation between our predictors needs to be in order for VIF to be a problem. And the answer is, I don't know. And probably a better answer is, well, it all depends. Here I've got a very simple curve that shows you the correlation between two predictors, x1 and x2, and VIF. And you notice that VIF, it's not bounded by 500. It could actually go up to an infinite value. But if you take a look here, these are values, and look, VIF doesn't really increase a whole lot. It's pretty flat all the way across until we hit this point where it's about 0.9, and then look at this step that it takes up. So this curve right here does increase. It is a positive slope. But VIF values are pretty low overall, and it's not that VIF is necessarily interpretable. What is interpretable is whether our hypothesis tests change based upon our multicollinearity problems. And here what I've done is I've changed the absolute correlation, right? Because sometimes things can be negatively correlated. And here's VIF. And I just jittered it because there's a lot of redundancy. And you can see that just with some small values of correlations, that all of a sudden we have an increase when we have correlations between two predictors of about 0.3. What we get is we get VIF values about 1.1. Well, what does all of this mean? It doesn't mean a whole lot, because what I want to know is I want to know more about whether the decisions change. And instead of looking at the VIF, now I want to look at, how about this? Let me look at the probability of x1 predicted by VIF. Perhaps, whoops. Okay, out. There we go. And look at here. So this is the probability. And you'll notice that here VIF, eventually there's going to be a relationship. As VIF increases, we expect the probability to increase as well. Why? Because VIF is, the probability here of x1 is nothing more than the p-value. And the p-value, this is 0.1, so that's still non-significant. Right here is 0.05. So we can have very small increases in VIF, and we can have non-significant values. Similarly, we can have 1.3 as VIF, and it's still significant at the 0.05 level. So what we need to do is, instead of looking for heuristics or rules of thumb, instead we need to be able to identify what the relevance of the variance inflation factor is, and whether the VIF is sufficiently large enough to potentially influence our non-significant findings. So let me rephrase that. VIF only becomes relevant when we fail to reject the null. When we fail to reject the null, meaning our p-values are greater than 0.05, we should start looking at VIF. And in particular, we should start looking at the correlation among our predictors. That if we have highly collinear predictors, or if we have multicollinearity as a problem, that multicollinearity may lead to a type 2 error, a failure of rejecting the null, not because there is no effect, but because we have an artifact in our model or in our data that inhibits our ability to reject the null. So multicollinearity does not affect parameter estimates. Multicollinearity affects hypothesis testing by inflating the standard errors and decreasing the value of t, therefore increasing the p-values, and leads us to a higher probability of type 2 errors. So from this point on, you should be more facile with the idea of what multicollinearity is about, going back to the assumptions that we discussed last week, why perfectly collinear predictors would be certainly a bad thing, and that multicollinearity decreases our statistical power. And with multicollinearity, we have to be very sensitive to the fact that even small correlations can lead to type 2 errors of the sort that we've examined with VIF. So there is no critical value of VIF. VIF is relevant when you fail to reject the null. There's no critical value, there's no heuristic, and there's even not a critical value between for correlations among your predictors. Instead, you must use your head. And this, I know, is unsettling for a lot of people, particularly students when they're learning statistics. They like these heuristics or rules of thumb that they can apply. But in this case, there is no rule of thumb that's going to be sensible. Use your head.